Oh, yes, that's my job. Sorry.
Thank you.
So the focus doesn't look incredibly good here. Is that usually the case? The focus doesn't look as good here as it does in the camera shot.
No, you want it to be good. I use the other control panel. I like the other one.
All right. Go ahead and set her up.
I use. That means it might be there somewhere. No, it's the advanced.
Sweetie.
Sorry.
Okay. Up there, it's 8 a.m.
It is.
Oh, go ahead. Go ahead. Yeah, no break.
Alrighty. Testing sound. Can everyone hear me okay?
Mine is buffering.
Okay. If there's anyone in the chat, can you chat that you can hear me? We just want to confirm before we get started. Thank you. Is that us, or do you think that's...
That was very late.
Okay. The sound sounds good, though.
Do you want me to end the stream and try to restart it?
I don't know. What do you think, Melissa?
That's really bad.
Okay. Maybe not.
All right.
There's no way it's going to catch up, right?
I can try refreshing my live stream page.
Yeah, try that. Is anybody?
Yes, they said it's fine.
Oh, okay.
How do I see the chat?
The chat's right there on the side.
They said it's really laggy. Yeah, they said it keeps buffering. It keeps freezing. Really laggy.
Mark, I think you can just refresh the page, and I think it'll be okay.
I can refresh this page. I doubt you can do that. We can restart this.
Yeah, Mark, I think although it's really bad, we should restart. It's very, very laggy.
Okay, I'm going to restart the router too. Okay, tell everybody to stand by.
Oh, wait, actually. Oh, it's good now.
Okay.
It has caught up to you?
Yeah, it's caught up.
Really?
Yeah.
You can
Okay.
hear-
Yeah.
You're live real time.
Wow, that was it.
Oh, yeah, that is close. Okay.
Okay, you're on.
All right. Hi, everyone. So you may notice that I am not Mark, and that's because today you're going to have guest lectures. It's going to be me and Melissa. So I'm going to start us off today. And yeah, welcome to lecture. Good morning. Today we're going to talk about the law of mass action and equilibrium. So let's get started. All right. So law of mass action and equilibrium. What we're going to look at here is we're going to look at reactions that come to like a macroscopic static stop. And so when we look at them macroscopically, it doesn't look like anything is happening because they've come to equilibrium. But microscopically, lots of things are still happening. So let's dive into that and take a look at it. So we're going to start with our reaction here. You have the colored capitalized letters, those are our reactants, and the lowercase letters are all of our coefficients. And those are really important because we're going to use them to measure whether or not things are at equilibrium and then predict like the behavior of reactions. So that's what we use this for. One of the things that we use when we talk about equilibrium coming to a stop, you're not seeing any changes, we use the reaction quotient. And the reaction quotient is going to be Q. And Q is something that we define as the products over the reactants. And so it is giving us a value for like the state of the reaction. When we look at the Q, it tells us what's going on in the reaction, where we're at. Why did it go backwards? That's okay. products over reactants. And we're going to put values into here. And so it's going to be like a number that we can calculate. And the values that we're going to put in are the concentrations to the power of the coefficients of the products and reactants. Now, one thing that I want to clarify and make sure that everybody knows is these bracket thingies. The bracket thingies, this means concentration. And concentration we measure in molarity, which is capital M. And molarity is equal to moles per liters. So brackety thingies, molarity, moles per liters. And it's telling you how much of something is in the solution because moles over the total liters. All right. I'm going to erase that one because I don't want it to be in the way. And so based on Q, if we look at Q and we look at what's going on in that number, we can determine what's going on in the reaction. And so already looking at it, something that you should be thinking is like, oh yeah, so if we have more products than reactants, Q is going to be greater than 1 because then the numerator is going to be larger than the denominator. If we have more reactants than products, then Q is going to be less than 1 because there we go. Concentration on the bottom as well. Q is going to be less than 1 if we have more reactants than products because the denominator is going to be bigger than the numerator. And then we can kind of follow and predict the behavior of reactions. So let's take a look at that on this graph here. We have a graph of concentration over time. And so now we're going to follow each it keeps going backwards with my sleeve, but that's okay. We're going to follow them in the reaction. So let's start with A. A and B, we're going to start with concentration. Concentration is going to be a number, not 0. And so concentration of A is going to start high and then decrease as the reaction goes on. Because in the reaction, we are consuming A to produce C and D. So same with concentration of B, we start high and it decreases because it is being consumed to produce C and D. And then this means we start with C and D having 0 concentration and they increase as the reaction goes over time because more products are formed. So you have our reactants and products. Reactants start high and be consumed and become less. Products start with low concentration and are produced and get higher. And then you'll notice here that these lines are leveling off. There's a point where A and B stop being consumed and C and D stop being produced. So what is this? What is this point? This is what we call equilibrium. The line where everything appears to not be changing on a macroscopic level, our concentrations remain the same. That is equilibrium. Concentrations, no change. You can wait forever, all of time forever, and the concentrations will not change because the reaction has reached equilibrium. And then, now that we know, so we have a point where we've reached equilibrium and we have points where we're not in equilibrium, we use our Q to determine the behavior. Oh, and then when we're at equilibrium, Q, or the concentrations are equal to K, which is our equilibrium constant. Q and K, we compare to each other, but so you always will have some value of Q. Wherever you are in the reaction, Q is a thing. And then when you reach equilibrium, the Q becomes K because K is the equilibrium constant. Kind of like, you know how delta G, every reaction has its unique delta G? Well, every reaction has its unique K, and the K will tell us what the concentrations will be when the reaction has reached equilibrium. Yeah, and then one more thing that I wanted to point out, just so you can remember the equilibrium expression better, is the coefficients. So we see here that our coefficients become our exponents, and if you think about that logically, if you need like 10 moles of B to react with 1 mole of A, then B is going to be consumed a lot faster, right? And so it's kind of like little b being the exponent there is telling us, oh yeah, this gets consumed a lot faster. So don't forget your exponents, because I promise you that there are homework questions and probably test questions that you're gonna have to understand and like write equilibrium expressions. So do that. All right, continuing on, we can compare Q to K to determine the behavior of a reaction. So in this area, before we've reached equilibrium, Q is going to be less than K. Now, why is that? So K is a point in equilibrium, but if we're in this area, Q is going to have more reactants than products because we haven't consumed all the reactants that we're going to consume, and we haven't produced all the products that we're going to produce. So there's still much more of A and B than there are of C and D. And if we look here, A and B being on the denominator, if we have more of A and B, Q is going to be smaller. And if we have less of C and D, Q will also be smaller. So when Q is less than K, what the reaction is going to do is it's going to shift to the product side, which we call the right. It's going to shift to the right. So it's shifting to the product side to produce more products so that we can get to K. So when Q is less than K, we produce more products and the reaction shifts to the right. When Q is equal to K, we're at equilibrium. Yay! When Q is greater than K, we know that we have more products than reactants than we would in equilibrium. And so Q with products on top becomes larger than it would at equilibrium. And so the reaction shifts towards the left side, towards the reactant side. And that right there, that's the law of mass action. The law of mass action is telling us when we're not at equilibrium, then the reaction is going to shift so that we can go back to equilibrium. And some situations you might see it come up in is, so if we were in this situation and then you came in here and you added C and you made the C line be bigger, then instead of the C line just increasing and being larger, what would happen is the reaction would shift so that everything could come back to this equilibrium. Law of mass action. Oh, I think I went backwards a bunch, but that's okay. All right. Now we're going to continue on to the next slide, where we're going to talk about dynamic equilibrium. And we talked about this a minute ago a little bit, but let's dive in deeper. Macroscopically, if you're looking at a reaction chamber that's in equilibrium, you're not going to see any change. It's going to look like nothing is happening. Think of, yeah, it's going to look like nothing is happening. You're going to look at it and you're like, oh, yes, everything's the same. There's no change. However, A and B are still reacting to C and D. There are lots of A and B molecules or particles that are converting to C and D molecules. And there are lots of C and D molecules converting to A and B. And so what's really happening is this reaction is just going back and forth, back and forth, back and forth between a lot of particles. And so macroscopically and with the net concentrations, they aren't changing at all. But individual molecules are changing. So it is not a static equilibrium. It looks like a static equilibrium, but it is actually dynamic because there are reactions forward and reverse happening the entire time, but they just happen at the same rate. And so our concentrations don't change. What's next? Oh yeah, cute. Okay, so there are lots of different types of reactions. I think I keep touching it. There are lots of different types of reactions. You've come across many of them so far, lots of different flavors of reactions. All reactions come to equilibrium. They all have some sort of equilibrium. So we're going to go through a bunch of different examples of how we see equilibrium in different reactions. Okay, so if we have concentration, let's look at that. our first reaction is aqueous. You may have heard the word aqueous before, and you may have seen the AQ abbreviation on maybe some homework problems or textbook readings. Aqueous is anything dissolved in water. And so this equation, which happens to be an acid-base equation, we will get to that. You don't need to know acid-bases specifically right now, but keep it in the back of your mind. Acid-base, we start with an acid, which is aqueous, dissolved in water, which is why it gives us a concentration, because concentration, again, is moles per liter. And so when we have something that's aqueous, it's going to be a certain number of moles in a certain number of liters of water. So aqueous things give us concentration, which is why they come up in equilibrium expressions so often. So in this one, aqueous acid and water becomes, this is a hydronium ion. We will get there. And that's also aqueous. And we also get the negatively charged acid, also aqueous. And so now what we're going to do is let's take a look at the equilibrium expression for this, and which, as you know, it's going to be products over reactants. So predict that in your mind, and let's take a look at it. If I can use the board. I might need help. I'll erase and pretend that that's going to do something. It did. Okay. So this is our equilibrium expression, and it might be different from what you predicted because you might notice that water didn't make it in the equilibrium expression, right? And so we have our equilibrium expression that has all of our aqueous things in it, but not water. And this is because we don't include pure solids or liquids in our equilibrium expression. Why is that? One, because the concentration of water in water is a constant. And so we don't really need to know what it is. It's just going to change the constant, and we use our K's and our Q's to compare to each other. And so the actual values are more important when they're relative. And so we can just leave the liquids and the solids out because they're just constants. They're constants in the Q and the K, whatever we're calculating. So we don't need them. But yeah, so our equilibrium expression for that, you have our hydronium ion and ionic acid on the top and our acid on the bottom. So only aqueous. Next, we will have a heterogeneous reaction, which means we have some sort of solid in our reaction chamber. And we're going from solid silver chloride to our silver ion and our chlorine ion. And again, here we have two aqueous things and one solid thing. And I'm about to show the equilibrium expression. Give a guess in your head as to what that's going to be. And it is, our K is equal to just the silver ion concentration times the chlorine ion concentration. And why is this again? It's because solids don't show up in our expression. And so the equilibrium expression for this is just the concentration of the products, because concentration of a solid over the solid is a constant. Next, we have gas phase. This one is a very important distinction. Going from, we have gases in there. Going from a gas to a different gas. If we have 2NO2 gas becoming N2O4 gas, neither of these are aqueous. And so how do we have concentrations of gases? What we do instead for our equilibrium expression is we do partial pressures. Because if you think about partial pressure and molarity, they're kind of similar. It's a fraction telling you how much of a certain species is present in a whole container or area. And so when we just have gases, we still do products over reactants because that's the magical formula. But we use partial pressures because that's what we have available to us for gases. And lastly, we can do a phase change. We can go from a liquid to a gas. And you might think to yourself, okay, I know this one. I'm ready. Liquid doesn't go in the expression. Gas, it's a partial pressure. Brilliant. You're correct. The equilibrium expression is just the partial pressure of the H2O gas. And that might ring a bell. You might be looking at that and be like, wait, I know what that is. Hint, it's the vapor pressure. So the equilibrium expression for a phase change going to gas is just the vapor pressure. Yeah, and if you think about a container, so I have a container here and it has water in it, and there's water and there's water vapor. That's an equilibrium. And the equilibrium constant is the vapor pressure because you have water and you have water constantly becoming like water vapor, and you have water vapor constantly becoming water, and the reaction is going back and forth and back and forth and back and forth, but it's going at the same rate. And so we are in equilibrium in our container of water and water vapor. And our equilibrium expression is the water vapor pressure. And then the last thing that we'll note here is that they have different notations. All of these different equilibrium constants have different notations to denote what kind of reaction it is. One thing to remember is that they are all still equilibrium constants. They are no different, but we just denote them differently. So Ka for K acid, because this one's an acid-base reaction in particular, you're going to be working with Kas a lot. And remember, Ka is just the K. We just slapped an A on there to help us remember, oh yeah, we're working with acids here. We have KSP, which is the K solubility product, because we have a soluble solid dissolving. And you may notice this is the only of our Ks here, of our equilibrium expressions, that is just multiplication and not a quotient. So it's a product, not a quotient. So it's the solubility product. And for our gas phase, we have Kp, which is K pressure, because we use the partial pressures. And the last one is also Kp, partial pressures. Vapor pressure. So that's the end of my segment. And so I'm going to hand it over to the fantastic Melissa. Here's a mic. We have switching. Oh, crap.
Do I just put this on my head? Why do women's pants never have pockets? Oh, it has a clip. Okay, perfect. Okay. Hello. So Ryann was very eloquent, so hopefully I can match up to her. But as Ryann was saying, when we write out the reaction quotient for this lovely reaction, the vaporization of water, we're actually using the vapor pressure, and we can examine that right now. So this is the same phase change reaction from the previous slide. We have water, liquid going into water, gas, so it's evaporating. And as Ryann was saying before, we can write this reaction quotient in terms of its partial pressures. So this reaction quotient is just going to be the partial pressure of H2O gas over 1, because we're in writing equilibrium expressions. We're just going to ignore all pure liquids and solids. Okay, I'll look at the camera. We're going to ignore all pure liquids and solids because they don't have constant activity or a constant concentration within our system. So our expression in this case is just going to be the partial pressure of water over 1, which is the partial pressure of water. And if we consider the fact that this is a pressure of water vapor over water, or in other terms, a pressure of a vapor over a liquid, this is essentially the same thing as our vapor pressure. So we can make the connection that our reaction quotient expression for this case is just going to be our vapor pressure of water. And we know that vapor pressure is just a function of temperature. So we can take a look at our PV diagram, which we should be pretty familiar with now because we've taken a look at this in the previous topics in units. But we know that at a temperature of 25 degrees Celsius or 298 Kelvin, we have a vapor pressure for water at 0.03 atmospheres. So if we were to plot this isotherm at 25 degrees Celsius, we can see that there's actually a plateau at exactly where the vapor pressure is. So if you're unfamiliar with this, you can go back to previous lectures and review this. But because of this, we know that our equilibrium constant is actually exactly at our vapor pressure, 0.03. So we can do the same by looking at a PT diagram. So now that we've looked at a PV diagram, let's look at a phase change diagram instead. So if we do the same thing and plot our vapor pressure at 0.03 atmospheres along this pressure y-axis, we can bring the line over and see that it intersects this yellow line between the liquid and gas at exactly 25 degrees Celsius again. So what does this tell us? Well, this tells us that at a pressure of 0.03 atmospheres and at a temperature of 25 degrees Celsius, we're at equilibrium between the liquid and the gas. But it's really important to keep in mind that this is just one point of many that can be in equilibrium between liquid and gas for water. So we can have equilibrium at this pressure and temperature, or at this pressure and temperature. Oh, I can draw it. At this temperature and pressure, or this temperature and pressure, or essentially any point along this line will be in between equilibrium between liquid and gas for water. So what if we want to find the reverse reaction? What if we want to find the reaction quotient expression for gas going to liquid? Oops. How do I get rid of this?
Use the back of the pen or eraser. I know it's super cool.
And then I...
That should be enough.
Please hold. Should I just erase everything? Sorry about the technical difficulties. I'm so technologically inept. Okay. So if we wanted to find the reverse reaction, instead the condensation from gas to liquid of water, we can notice that our reactants are now our products and our products are now our reactants. So what does this mean in terms of writing out our expression? We would just find the reciprocal of the reaction expression that we've written before. So instead of our Q equaling the partial pressure of H2O, it would equal 1 over our partial pressure of H2O. So we would just find the inverse. And this would, again, equal 1 over our vapor pressure. So let's now apply what we've just learned with a chem quiz. So here we have the same reaction from the previous slide. So we have H2O liquid going into H2O gas. So we have the vaporization of water again. So which is true under standard conditions? So keep in mind what standard conditions are, and then why don't we go into our breakout rooms and discuss this? And I'll bring up the 4 slides again. How do I mute? Responses in. So sorry about the fact that some of you couldn't see the question, but hopefully you guys were able to get your answers in anyway. So let's take a look at what you guys thought. So 36% of you thought A, which was Q is less. I don't even remember the answer choices. Yes, Q is less than K. And most of you, 50% of you, thought B, so Q equals K. And there were a minority of you that chose C. So let's go through this together. Nice. Wow. Okay. Okay, so again, the question is, which is true under standard conditions? And we have the vaporization of water. So from the previous slide about vapor pressures, we already figured out that the equilibrium constant for water is equivalent to the vapor pressure of water. And what was that again? It was 0.03, because at 25 degrees Celsius or 298 Kelvin, we had a vapor pressure of 0.03 atmospheres. But we have to remember what standard conditions are in order for us to compare the two. So what do we have at standard conditions? Well, we have reactants and products that are all at 1 molar. If we have gases, then our gases are all at 1 atmosphere. And if we have liquids and solids, they're going to appear as pure liquids and solids within our system. So what does that mean for our reaction quotient, Q? Well, that means Q is going to equal to 1, because at standard conditions, we're at 1 atmosphere. And K, again, equals 0.03. So as you can see, Q is much greater than K. So our answer would actually be C. So the minority of you got it right. So good job. So if Q is much greater than K, if we think back to Ryan's first slide, then we're actually going to go in the reverse reaction. So our reaction would go backwards. And this makes sense because at 1 atmosphere, you would assume that water would condense from a gas to a liquid. Okay, so let's move on to a second chem quiz, and we'll go through this one together. So we have the same reaction here, which is the vaporization of water. So in this case, we're thinking about our equilibrium constant and temperature. So how does K vary with temperature? And we see that we're given a phase change diagram to reference. So again, if we think back to the original vapor pressure slide, we said that any point along this yellow line between liquid and gas is a point where pressure and temperature, any pressure and temperature along this point, we can have equilibrium between liquid and gas. So we also talked about how in this case, the partial pressure of water is going to equal our vapor pressure, which is also equivalent to K, which is going to be a function of temperature. So what does this mean in the grand scheme? Well, it means that our equilibrium is going to be any point along this yellow line. So that gives us C as our answer. So instead of pressure, we're just interchanging it with our K value, because our K value is essentially the same thing as our vapor pressure. So as Ryan was saying before, if we take a look at equilibrium macroscopically, we see no change in our reactants and products concentrations. However, if we take a look at equilibrium microscopically, we can tell that there is reactions going forward and there are reactions going in the reverse direction at equal rates that cancel each other out. So we can approach equilibrium in several different ways. So if we take a look at this thermodynamic landscape or landscape of stability, oftentimes reactions will sit at thermodynamically unstable states. So they will sit on top of this thermodynamically unstable hill until a reaction allows them to proceed to a more thermodynamically stable state. So in these thermodynamically stable wells. And this is true for the formation of water. So if we form water from H2 and O2 gas, hydrogen and oxygen gas, hydrogen and oxygen gas are actually thermodynamically unstable themselves, but they can sit in a balloon for almost eternally if we don't do anything to it. So kinetically, they're pretty stable. But the more stable state is actually forming together to form water or H2O. So unless we were to explode the balloon and pop it or light it on fire and form water, we wouldn't get this transition from an unstable to stable state. So what we're saying here is that in thermodynamics doesn't tell us anything about the rate of reaction, but it does tell us about whether or not products are favored or not. So even though this reaction from H2 and O2 gas has a very large K value forming water, it doesn't typically form water because it'll stay in this specific state of gaseous state. So we can take a look at several different approaches to equilibrium, and one of them is monotonic. So in a monotonic approach to equilibrium, we have a graph here, and our partial pressure or concentration of our reactants or products are on our y-axis, and we have time on our x-axis for every single one of these next graphs. So in a monotonic approach, we have our products starting from a very low quantity and slowly increasing and leveling off at a concentration or partial pressure. And then if we think about our reactants, we would have the same. So our reactants would start from a high quantity and decrease and level off. So this is probably the most common approach to equilibrium that you'll see, but there are several different ones that we can observe as well. So we have a clock approach, which we can observe Mark doing in this echem video. How do I turn the volume? So as you can see, Mark is adding, he's already mixed together the two reactants, and he's counting down. Oh, I wish you had the voiceover for this. And as you can see, the product changed from a translucent color to a blue color here. So you can see that the products initially start out at a very low quantity and then suddenly jump and plateau. So that illustrates a clock approach pretty well. Next, we have an oscillatory approach where we have an oscillation of products. And we can see that in another echem video with Mark. So as you can see, Mark is now mixing the two reactants together in this beaker on a spin with a spin bar inside. And it turns blue almost immediately. But if we wait a little bit, Mark is counting down now. 3, 2, 1, it turns back clear. So it's going to turn back blue again. So as you can see, we have this oscillatory product concentration where we first start off at a very limited quantity and then jump up and then down and up and down again. But if we notice, the envelope or the general trend of this oscillatory approach is exactly the same as the monotonic approach. So we start with very limited product and we eventually level off into equilibrium. Okay. And finally, we have a chaotic approach, which is very similar to oscillatory, but with oscillatory, we can probably visualize this with an equation. But with chaotic, we can't really predict what's going to happen with the concentration of reactants or concentration of products. So in this case, you see we have very high, very low jumps. But again, the envelope is very similar to monotonic, where you start off with very little concentration of products, and then you increase and level off into equilibrium.
All right, hi everyone. I'm back and I will be taking you through this chem quiz here. So think back to gases and the gas equilibrium that we were talking about earlier. For the reaction, I2 solid to I2 gas, so we're having diatomic iodine going from solid to gas. What happens to the vapor color intensity when I2 solid is added? So think about it. Go for it. To note for everyone, it is a sublimation. It is a solid going straight to a gas, which is still an equilibrium thing. Still a vapor pressure. So we're going to bring it back together. So click your button, put a guess in. Remember that we don't grade you on correctness, so click A button. Please don't click to your E. That doesn't help you. All right. We're going to look at the results now. All right. And we are looking at A. A lot of people think it's going to be A increases. So we think that when we add more solid, we're going to get an increase in color intensity. So let's take a look at that. All right. So iodine gas, we have our equation here. We have iodine solid becoming iodine gas. Let's talk about intensity because I heard that there was a little bit of confusion going on with that. Color intensity is due to the gas. And so if you have a higher vapor pressure of gas, it's going to be there's going to be more color intensity because more gas will give you more color intensity. You know, if you had just a little bit of gas and a lot of air and it's a pink gas, then it's going to look not very pink. But if you have a lot of the pink gas in clear air, it's going to be very pink. So color intensity, we are looking at, we want concentration, but it's not concentration, it's the vapor pressure. So more gas, more color. All right. So then, is that backwards? Yeah, I just don't know how to use a board. That's fine. All right. So let's talk about our equilibrium expression. And remember that our equilibrium expression is going to be just the vapor pressure of iodine gas. And my real question for you is, does this ever change? And the answer is, as long as we're staying at the same temperature, the vapor pressure never changes. And so our equilibrium is never going to change. And so we're always going to come back to this equilibrium. And so if we add some solid, then that's going to shift our Q, right? That's going to change the value of our Q. Oh yeah. Oh crap. Solid does not appear. I was totally wrong. So if we add more solid, that doesn't change our equilibrium expression at all. And so no more gas is going to be produced. And so actually, vapor pressure of I2 stays the same. It's independent of the solid. And so it doesn't change at all. The intensity is going to stay the same because we know that solids don't come up in our equilibrium expression. And so it doesn't have an effect on anything. All right. And then the next one that we're going to do, and we will just walk through this one. So we have iodine solid and iodine gas, same reaction. What if we heated it up? We have what happens to the vapor color intensity when the temperature is raised? Make your guesses in your head, but we're not actually going to do this one in a quiz. We'll just go over this together. What happens when temperature increases? Well, let's go back to our pressure and temperature space of vapor pressure. And we know that if something is in equilibrium, it's going to fall along, solid and liquid. Nope, solid and gas is going to be on this line. We are sublimating, and so we are in equilibrium between solid and gas, which means that we're going to be along that line. And we know again that the equilibrium expression is just equal to the vapor pressure of iodine. So what happens when we increase the temperature? Well, temperature increase is going this way. And so if we had our dot starting here, we're starting at a temperature and we increase the temperature, then this dot is going to move along this line, be somewhere up here, which we'll call this one P1 and we'll call this one P2. And so we're coming to a higher pressure. And so our vapor pressure is going to increase as temperature increases. And given that our equilibrium expression is just equal to the vapor pressure, that means that our equilibrium constant K is also going to increase. And because of that, we know that K is also equal to products over reactants. And so if K increases, we know that either or both products are increasing and reactants are decreasing, because that's how math works. In order for K to increase, the numerator is getting larger or the denominator is getting smaller. And so we are increasing in products, decreasing in reactants, which means that our reaction is shifting in that direction, which means that our intensity of the light or of the color is increasing because we are increasing in pressure, in partial pressure of the vapor, of the gas, which is the one responsible for the color. And our answer is increasing. And then I think that is the end of the lecture. So we've made it through without any major disasters from Melissa or I. Woohoo! And since there's more time in class, we are going to hand it back to Mark, who will rescue us, truly. Oh yeah, mute.
Morning, guys. That was awesome. I'm glad to see the student instructors stepping up to the plate here. One reason, of course, they're great at it. The other reason is, as you know, my voice has just been really trailing off. Hopefully, if you guys are in Jiho's discussion section, you can kind of work on him. And he lives in Tracy, which is really hard drive in the morning to get here at 8 o'clock. So it would be a stretch for him, but we'd really like to see him come and do a guest lecture as well. Because if you're in his discussion section, you know how good he is at presenting. But gallery clap for the girls who were here today. That was awesome. So we'll continue with what we're discussing, and I'm going to try to keep my voice monotone. I think what I do, I talk for 90 minutes a day here, and then Zoom meetings the rest of the day. Here I get really excited, and I think I just stress my voice. So I'm going to try to be less like Bernie Sanders and more like Barack Obama. So let's try that. So we've seen equilibria so far, and our concept is these two gases. This is a brown gas NO2 dimerizing to N2O4. If this is an equilibrium, the concentrations macroscopically, the partial pressures of each gas don't change. However, the NO2 is converting to N2O4 and the N2O4 converting back to NO2. There's a dynamic process going on. It's just that the rate of going backwards is the same as the rate going forwards. So the concentrations don't change. Every time an NO2 dimerizes, two NO2s dimerize, and N2O4 breaks apart. So the color intensity, this one's brown and that one's clear, in this particular situation wouldn't change. So that's the nature of K. The partial pressures overall aren't changing. We can't see anything happening, but there's a dynamic process going on underneath. And we can influence that dynamic process. And we've seen it already. Temperature is one thing that influences that dynamic process. Vapor pressure is a function of temperature, and in general, K is a function of temperature. So it's an equilibrium constant, but the constant is different for different temperatures. So you'll still get to a point where the products and reactants macroscopically aren't changing in concentration or partial pressure. You go to a different temperature, they'll go to a different place where they don't change in macroscopic concentration. So equilibria are established at specific temperatures, but can change with temperature. So for this particular reaction, K is a modest value, around 7. It's exothermic going in this direction. So you have the dimerization going in that direction. You expect that to be exothermic. The reaction expression, the equilibrium expression, is the partial pressure over the products over the reactant. And remember, we need the stoichiometric coefficient of 2 here. Raise the partial pressure of NO2 to the power 2 in the denominator. And at equilibrium, that stops changing for every specific temperature. So let's look at that happening. So let's say the volume is doubled. So you have NO2 and N2O4 in one side of this flask. You open this valve and let the gas expand into the entire volume. What does that do to the position of the equilibrium? Does it move it towards products or does it move it towards reactants? So you've disturbed the equilibrium, and you know intuitively, and now I hope you know quantitatively, if you change the volume, partial pressures change. So immediately you go from equilibrium to not equilibrium. And how would that affect the intensity? So let's talk about this one for a minute and back and discuss it as a group. nice stop. Okay, so you've had some time to think about that one. Let's see what you're thinking. Ryann will show us her screen, and she has a result of decrease, and it's really popular. So let's talk through that together. So you'll write the equilibrium expression, and you can write the equilibrium expression all the time. You can put any partial pressures in here. And when you put any old partial pressure in there, that'll give you a reaction quotient. It may or may not equal the equilibrium constant, but we know the reaction will shift until it does. It's this crazy aspect of nature where you put products and reactants together, they will reach this equilibrium, and it's always the same number. And it's a crazy thing because you could start with all products, you could start with all reactants, you can start with any mixture of products and reactants, and they will still rearrange to have this ratio of products to reactants. So we have this expression. We can derive the expression, believe it or not. It does come from the entropy of, if you look at microscopic entropy and in tiny little steps of going from products to reactants, and you actually arrive at this expression. So it doesn't come from nowhere. It's thermodynamic. There's a thermodynamic basis for it, but it's still just really kind of cool and intuitively not obvious that wherever you start, you'd come to the same ratio. But it's an interesting fact of nature. And if we had time, and if you go on in chemistry and take more chemistry, you'll actually end up looking at that in more detail. What we did is we doubled the volume. So when we double the volume, we reduce the partial pressures of each species by a factor of 1/2. So the partial pressures both immediately drop because they had twice as much space to occupy. But you can see, because the partial pressure of NO2 there's a squared factor there, I'm going to get a larger factor in the denominator, a 1/4 factor in the denominator, which will make K increase by a factor of 2. So a little bit of very simple math: square 1/2 in the denominator, you get a 1/4 in the denominator that comes up into the numerator, multiplies by that 1/2, and you find K twice. You've gone to a factor of 2 times K. So in that case, you'd say the equilibrium position goes to a point where Q is greater than K. So this in general is called LeChatelier's principle. And you know that I hardly use anybody's name in this class. I don't want you to remember equations based on a name. We don't use Boyle's law or Charles' law or Hess's law or anything like that. I want you to remember the concept and not the name. LeChatelier's principle, though, is so ubiquitous that I have to tell it to you, because if you go anywhere else in chemistry, they're going to use that, and you'll have to know that language. But it's just the principle we're talking about here. Equilibria are dynamic. The reactions are always happening in forward and reverse directions. So if there's a perturbation, if you change temperatures or pressures or volumes, or you add a product or you add a reactant, the equilibrium is dynamic, so it will adjust itself. So that ratio, that fixed ratio expression that we call the equilibrium expression, the products and reactants rearrange themselves to come back to that same ratio, that same value of K. So we just saw that happen. Q can be equal to K. That means you are at equilibrium. And remember, when we say Q is equal to K, we're just saying that you're at equilibrium. The equilibrium expression, you plug in all the numbers, it's a constant. We can catalog these values so you can look up the values of K for various reactions. So you can tell if you're at equilibrium or not. Or you can say, if I run this reaction, will it go towards products at all? Is K large? If K isn't large, the reaction isn't going to make a lot of products. So there's a question of why do it? So reactions that don't proceed, you mix two things together and they don't proceed, it may be because the equilibrium constant is very small and reactants are favored. It could be the situation, though, that the reaction doesn't go for kinetic reasons. That is, there's not enough energy in the system for the reaction to go. So there's a lot of reasons why you wouldn't reach products. But if K is large, theoretically, if you're going to get there, you're going to get a lot of products. If K is small, don't bother, because even if you overcome all the kinetic barriers, you're still not going to get a lot of products. So we did this example here where we changed the volume. So we had the right mixture. We had an equilibrium mixture where the ratio was satisfied, the expression K, we're at equilibrium. We doubled the volume, and now the partial pressures decreased. So what happens is, well, you can think about it intuitively. If the pressures decreased, what's the system going to do? The system is saying, I suddenly have more volume that I can expand into. I can take up more space. Well, which side of the reaction takes up more space? The NO2 side. You can form more particles. You can take up more space if you just break up more of the dimers. So you can make more total particles if the reaction shifts towards a greater number of the NO2 particles. So you can have that shift from a situation where Q is equal to K. You change the volume, the partial pressures change, but then the partial pressures shift themselves to get back to that magical ratio. So the process of nature is get to this number K by hook or by crook, however you can do it. In this case, it's kind of intuitive because you say, got more space? Let me shift to the side of the reaction that takes up more space and fill up that space. And that's back towards the reactants. So I'll shift back towards the reactants until that ratio is equal to K again. That's the beauty of this K thing. You know where it's going to go. It's going to end up at that ratio of K. So let's talk through one. We're going to reverse blood poisoning. And I know many of you are interested in biology and medicine to start with, and we'll talk a bunch about it. Our acid-base chemistry is coming up, and acid-base chemistry crucial in biological chemistry, and the LeChatelier's equilibrium are crucial in biological chemistry. So here's just an interesting question, and you can think about it as a first approximation by this LeChatelier's principle. So what would you do to reverse blood poisoning, carbon monoxide blood poisoning? It turns out that carbon monoxide binds much more strongly to hemoglobin. So I've put hemoglobin here. I've just called it HB. It's a big molecule that binds to oxygen and carries oxygen from your lungs to your cells. So hemoglobin, this large molecule, it has a complex with oxygen. So it binds some oxygens. But if carbon monoxide is around, carbon monoxide binds more strongly. And if you if you're breathing in carbon monoxide, it displaces the oxygen, and you essentially suffocate. Even though you can breathe in and out, your hemoglobin can't carry the oxygen to your cells because carbon monoxide displaces it and it binds more tightly. The oxygen can't get in there and be carried to your cells. So you could predict the size of the K. And you can say, is it bigger than 1 or less than 1? If I just tell you that fact, carbon monoxide binds more strongly. So if carbon monoxide binds more strongly to hemoglobin, K is going to favor products. The product concentrations are going to be larger than the reactant concentrations. So K is greater than 1. It's about all we can say. Can't say about how big it is, but the bigger it is, the stronger the binding would be. But you know that it's not a fraction. You know that products over reactants, the reactants aren't bigger than the products. So you know it's greater than 1. So which of these would I, which strategy would I reuse? Increase the partial pressure of oxygen, cool everything off. That is, change the reaction by changing K, by changing the temperature, or remove some hemoglobin molecules, which will make it reverse. And of course, reversing blood poisoning, you want the reaction to go back here to get your hemoglobin binding oxygen again. So how do I make this reaction go back towards reactants? Well, I need to add something that increases on this side to make it go to this side. So I need to add something here that will force me back to this side. And I can add more oxygen. Adding more oxygen is a product. It's going to make Q bigger than K, and we're going to shift back towards reactants to bring that Q value back down to K. So that's the essence of LeChatelier's principle. So if you are experiencing carbon monoxide poisoning, first of all, get out of the area where there's a lot of carbon monoxide. But the oxygen mask, when the paramedics come, get that oxygen mask on you right away, increase the partial pressure of oxygen in your lungs, and force this reaction back here, expel the carbon monoxide from your body. We're going to increase the partial pressure of oxygen. That'll decrease the pressure of this and increase the concentration here. So making it big here, I have more of these to react with these. That'll drop the concentration of the carbon monoxide bound hemoglobin and increase the oxygen bound hemoglobin. So temperature and equilibrium, we'll talk through this one too. What happens to the color intensity when I increase the temperature here? So what do you need to know? And this is one of those things that might show up on the exam, and I might not tell you whether this reaction is exothermic or endothermic. Is that fair? It was actually on a previous slide. But is it fair for me to say that? Well, the only thing that's happening in this reaction is I'm forming a bond. I go to a monomer to a dimer. I form a bond. And if you take nothing else home from Chem 1A, take home the fact that breaking bonds always takes energy. Forming bonds always releases energy. I could just show you this reaction and kind of expect that you would know that. The only thing that's happening here is a formation of a bond, monomer to dimer. So I could also just show you this and expect you to know what the relative entropy change is. So this is exothermic, is an increase in entropy or a decrease in entropy. I don't have to give you a table or show you anything because you can see I go from 2 particles on this side of the reaction, I reduce the number of particles. And whenever you reduce the number of particles, entropy is an extensive property. It depends on the number of particles that reduces the entropy. So there's things you can deduce here, and I need you to be thinking about those fundamental principles and not rely on numbers all the time. You could go to a table, you could get the standard enthalpies of formation of those two and calculate that it's exothermic. So if it's exothermic, what happens to the color and temperature when the temperature is raised? Well, if it's exothermic, you could say that heat is essentially a product, exothermic reaction. And then you can apply your LeChatelier's principle again. If heat's a product, then the addition of heat is essentially an adding of a product, and that shifts the reaction back towards the reactants. So this would get darker because the NO2 is the dark gas. But we've seen that already. We've seen these vapor pressures. And you know, a vapor pressure. If I take H2O liquid and I go to H2O gas or iodine solid and go to iodine gas, the K for these reactions was equal to the vapor pressure. And we know how the vapor pressure varies with temperature. If you get to a higher temperature, the vapor pressure will increase. And we know these reactions are endothermic. I had to take heat, put it into there to break those intermolecular reactions and go to here. I know they're endothermic. K gets bigger with temperature because heat in the endothermic reactions is over here. Let me just put Q over there. And that forces the reaction. Same idea, a LeChatelier's principle goes to gas, more gas, higher vapor pressure. The reason it didn't shift when I added solids, we talked about, does the iodine get darker when I add solid? The answer was no, it doesn't. We'll erase some of these things up here. If you write the equilibrium expression, put our iodine solid back in there, the equilibrium expression is K equals, well, it's going to be products over reactants, but if your reactant is a pure solid or a pure liquid, it does not appear. So K is just the partial pressure of iodine. Adding more solid does not affect Q or K. It's not there. So vapor pressure is independent of the amount of solid there. Basically, if you add more solid, sure, you'd think, oh, that's going to make more vapor. That'd be your first impression. But you're adding more surface area of the solid. So you have more opportunities for the gas to condense back into the solid phase. That's essentially why that does not, the solid amount of solid does not appear in that expression. So I can add heat. This reaction, force it back to the products. That's going to get darker. There I've written it out, and that's the general expression. So let's look at that. This is important, but we understand it now. For exothermic reactions, K decreases with temperature. For endothermic reactions, K's increase with temperature. And we can see that using kind of a LeChatelier's principle approach and having the heat as a product in exothermic reactions and heat as a reactant in endothermic reactions. So here's a very important equilibrium expression. This all in the gas phase. This is fixation of nitrogen. So you take nitrogen from the air, essentially, combine it with hydrogen to get a compound you can use to make chemical reactions, to do chemical reactions. Nitrogen in general is not reactive. It's the largest component of the air. 70% of the air is nitrogen, but it's not a very reactive molecule. That triple bond is a strong bond. Nitrogen doesn't react readily with very many things. But we need nitrogen for two reasons. One, it's really important in our fertilizers. So it'd be nice to be able to get it out of the air and put it into the ground. And the more the more sinister, the other reason is nitrogen compounds are common precursors to explosives. So there was a lot of effort, unfortunately, in World War I to make this process go, to get some nitrogen so I could make dynamite. So the motivation for this wasn't fertilizer originally, it was to make dynamite, but this process, they used the idea that I want to force it that way. How do I force it that way? Well, the reaction is exothermic. So it's slow at 25 degrees C, but high temperature means K gets lower, so that doesn't help us to raise the temperature, so raise the pressure as much as you can. If you raise the pressure as much as you can, this side is the higher number of particles. 4 moles of gas on this side, 2 moles of gas on this side. So squeezing this thing, the whole system wants to go to the area, reduce that stress. How do I reduce that stress? Well, I can make fewer particles. So I can force the equilibrium. So the actual conditions, 500 degrees C and 200 atmospheres of pressure to make that reaction produce this ammonia. Shift the equilibrium. It takes these extreme conditions. We had the fact that it's exothermic. Exothermic wasn't helping us. That would force it back this way, but it turns out that you still go to relatively high temperatures, and that's due to a kinetic effect. It's not a thermodynamic effect. We'll talk about how those balance later. But the very high pressure we can understand. Force it in that direction, force it towards products. So equilibria can occur together. If you have common reactants and products, the equilibrium of this reaction, A going to B, will affect B going to C, of course, because the concentration of B is affected by both being able to convert to A and convert to C. And of course, if there's another reaction taking up your A and converting it to C, then the concentration of C is affected by both this process and that process. So all the equilibrium together at once, this can get quite complicated, but the values of K help us sort it out. So if we have the equilibrium constants for the individual reactions, and we notice that if I write the reaction A going to B and the reaction of B going to C, I can predict what the reaction A going to C is, because the sum of these two is A going to C. So if I add those two reactions together, how do I treat the K's to get the equilibrium constant for the final reaction, A to C? Well, how do I get K3? Well, you'd notice if you write an expression, K3 is actually equal to numerically, functionally, C over A, the concentration of the products C over the reactants A. But you could multiply top and bottom by B if you wanted, concentration of B. And if you do that, you're going to notice that that is the equilibrium expression, products over reactants for A. That is K1. And that's products over reactants for the second reaction. So it looks like K3 is K1 times K2. And that's actually the case. So if you have multiple equilibria and you can treat the reactions in this format, add them together, combine them to form one of the possible processes, then you can calculate and interchange Ks by the fact that if you add reactions, you multiply equilibrium constants. You know already that if you add or subtract reactions, you add the enthalpies. So add enthalpies when you add reactions, multiply equilibrium constants. So here's an interesting one. Think about this for just a second. We'll start a chem quiz. If you're ready, Ryan, we'll just take the last few minutes of class to think about this, because this is one of those situations where I'm not telling you what delta H1 and delta H2 are, but I want you to predict what K is as a function of T. So for the molecular rearrangement I've shown here, I have essentially you could call it an isomerization, you could call it a resonance interaction. How does K depend on T? Increase, same, decrease. Think about that for a second and take a vote. So just a little help, the reaction we're showing there, you could assume all the bonds are being broken and then being reformed. Okay, guys, in the interest of time, I'll interrupt your discussion so we can wrap up here. I'll go back to Ryann. She'll show you what the vote is. We have no idea. And this is one of those times where you have to think about what's happening and kind of extend your reasoning just a bit. The reason we do this as a chem quiz is I don't want to tell you everything. I want you to anticipate some of the things that are happening. So what is going on here? Well, what I wanted you to realize is that delta H1, all I did there was kind of break all the double bonds, and then I reformed all the double bonds. And in fact, A and C are the same molecule. They're just rotated by one direction, but not the band, the actual process. So is it one direction? So, but if I had delta H1 and that was the breaking all of the bonds, that would be endothermic, but delta H2 remaking them would be exothermic in exactly the same energy. So delta H1 and delta H2, which is A going to C, delta H1 and delta H2 are zero, add to zero. So the enthalpy change for this reaction is zero. And we were saying the enthalpy determines how K varies with T. So in this kind of artificial reaction, K is not a function of temperature because it's neither exothermic nor endothermic. And in fact, it is just a molecular rearrangement and kind of an artificial one. I kind of made this up to emphasize the fact that you could look at the process, you could think making versus breaking bonds, you could come up with that enthalpy is equal to the opposite sign of that enthalpy, and then say, well, enthalpy determines how K varies with temperature, and you'd have to end up saying, well, it's neither endothermic nor exothermic, so K probably doesn't vary with temperature. Okay, that is it. It's Thursday, so I can take a couple questions. The exam is on Monday. The exam will cover what we've ended here today. So LeChatelier's principle, multiple equilibria, and what Melissa and Ryan talked to you about, the law of mass action earlier. And it'll be the same format, around between 40 and 50 questions and an hour and a half to do it. So are there any questions? They're going to hang around a few minutes, right? Okay, so as soon as, if there are no questions, we'll go right to them.
Okay.
Or do we have any questions coming in? You can tell that, Melissa, we're going to go right to them, and we'll try to get a recording. What I'd like to do, as I told you, I'd like to try to run Zoom here. So what we'll do is we'll have a discussion. We can have the Zoom open, and they can be telling us what they did this week in terms of picking clips and that kind of stuff. So yeah, if there are no questions, but let's end the live stream and start a new one. Okay, there weren't a lot of questions, guys, so we're going to sign off. We're going to kind of talk to one of the discussion groups here. Won't be about chemistry, though, so we'll see most of you on Monday for a review and the exam Monday evening.